High-strength gears are pretty much the unsung heroes working away inside our most powerful machines. I mean, they're marvels of engineering, right? Built to handle incredible stress. But sometimes, even with all our best efforts, they fail, and they fail catastrophically. So today, we're going to play detective and find the hidden culprit behind it all.
Just look at these things. They are precision engineered to transfer massive amounts of torque, and everything from giant industrial gearboxes to the transmission in your car. Their whole job is to withstand unbelievable forces, day in and day out, without ever giving up.
And to get that kind of strength, they go through a special process called case-hardening. This creates this ultra-hard, wear-resistant surface layer. It's basically like giving the steel its own suit of armor, designed to guarantee a long, reliable life.
So yeah, that's the million-dollar question, isn't it? If these parts are so tough, so carefully designed and treated, what on earth could cause them to just suddenly break apart, sometimes after only a short time in service? Well, the answer is hiding where you'd never see it.
Okay, so our investigation kicks off with the evidence, a failed component. By taking a close look at the fracture, we can actually trace the failure all the way back to its origin, and hopefully figure out what went wrong.
So check this out. This is a crown wheel that failed after a really short time on the job. And notice how cracks appeared on multiple teeth? That tells you this wasn't just some random accident. It's a symptom of a much deeper, more fundamental problem inside the material itself. To find the real villain here, we need to go from the scale of centimeters to micrometers. We have to zoom in. The fatal flaw is completely invisible to the naked eye. A tiny traitor hiding deep within the steel.
So, using a scanning electron microscope, investigators zeroed in on the exact origin point of the fracture. The image on the left, that's the microscopic starting point. But the graph on the right? That reveals its chemical makeup, and those peaks for aluminum, oxygen, calcium, that's a dead giveaway. This isn't steel, it's an impurity, a weak spot embedded right in the metal.
This little troublemaker is called a non-metallic inclusion. The easiest way to think of it is like a tiny piece of slag or ceramic dust that got trapped in the liquid steel while it was cooling down. Now, these inclusions are just a part of making steel, but their size, their shape, and where they end up, that can be the difference between a reliable part and a total disaster. That chemical fingerprint we just saw tells a really clear story. These elements, aluminum, oxygen, calcium, they're typical of the slag residues from the steel production process. They're basically foreign bodies that mess up the strong, uniform crystal structure of the steel, creating the perfect weak point.
But here's the thing, and this is absolutely crucial. Not all inclusions are created equal. Some are kind of rounded and relatively harmless. The most dangerous ones, though, are sharp and angular, like alumina inclusions. Think of it this way. A round pebble in concrete is probably fine, but a sharp piece of glass creates a natural breaking point. Well, these sharp corners do the exact same thing. They concentrate all the stress on one tiny point, acting as the perfect launch pad for a crack.
For decades, finding these tiny, dangerous defects was a slow, painstaking manual process. But now, we have a new tool in our arsenal: artificial intelligence. We can now train an AI to be a tireless, microscopic detective that never gets tired and never misses a thing.
This is a huge shift in how we do quality control. We're moving from a reactive world, where we analyze parts after they break, to a proactive one. Instead of relying on manual inspection, which can be slow and inconsistent, we can now use AI to analyze huge amounts of data and predict the risk of failure before a part even leaves the factory.
So how does this AI detective actually work? Well, the pipeline starts by just eating data. It ingests everything: the steel's chemistry, the parameters from the furnace, thousands of microscopic images. The AI then learns to identify and classify what it's seeing, from the steel's grain structure to those dangerous little alumina inclusions. And from there, it can predict the final mechanical properties and, most importantly, flag a batch of steel that poses a high risk.
And this is where it gets really powerful. We're moving beyond just predicting problems to actually preventing them. The real power of this tech isn't just finding flaws, it's stopping them from ever causing a failure in the first place, with incredible accuracy and speed.
Just look at this number. AI models can analyze a metallographic image and correctly classify the steel's grain structure with over 96% accuracy. I mean, think about that. That level of precision, done automatically, consistently, 24/7, it's a total game changer for quality control.
And then there's the speed. It's just no contest. What might take a human expert several minutes to analyze, an AI can process in less than 10 seconds.
When you're dealing with thousands of samples, that massive boost in efficiency means you can monitor quality in near real time, not just do a few spot checks here and there.
But the AI doesn't just see what's already there. It predicts the future. Using these powerful machine learning models, it can forecast the final mechanical properties of the steel with stunning confidence. That R-square value of over 0.95, in plain English, that means the AI's predictions for things like hardness are practically spot on with what you see in real-world tests. It lets manufacturers tweak their process to make the perfect material every single time.
So, as you can see, this is about way more than just making better gears. By integrating AI into one of our most foundational industries, we are fundamentally changing how we design, manufacture, and even use these critical materials. And this isn't just a theory, by the way. This is happening right now, in the real world. At huge facilities like Tata Steel, putting these AI-assisted systems to work has led to a dramatic 60% increase in quality yields, a big reduction in fuel use, and millions of dollars in savings every year. That's the real return on investment for making steel smarter.
There's a quote that I think just nails it. For centuries, making steel has been part art, part science, kind of a black box where you rely on experience. AI gives us the tools to finally open that box, to make the whole process transparent, data-driven, and way more efficient and sustainable.
Which leaves us with a really fascinating question for the future, doesn't it? We've seen how AI can completely transform an age-old material like steel, preventing failures before they can even start. So what happens when we apply that same intelligence to ceramics, to polymers, or to the next generation of composite materials? The possibilities, they're truly revolutionary.